Welcome to this lecture on transient heat and mass transfer, mass being moisture or air, because there are some analogies, and those analogies I will bring even further back in physics. You may have heard for electrical charging of a capacitor of such an RC network, as I will shortly explain. We have a capacitor here, which is charged electrically when it's connected to the battery here, so a voltage supply. When we draw the switch here, it connects through the resistance, the electrical resistance here, and we measure then the voltage over the capacitor with this VC. That's an equation that explains it, how it develops over time. VC is a fraction of the supply voltage, and that fraction is written here in a parenthesis, 1 minus the exponential of something with the time, it's minus the time, divided by the resistance and the capacitance in product, the product of those two here. So this is our equation for the RC network, the development over time, as we can also draw here. So the voltage, if I draw it versus time, it starts at 0 voltage, and then it approaches with time gradually more and more, coming close to the eventual value of the supply voltage from the battery. We have a notion of something that's called the time constant, which is the time it takes until 63% of the final voltage has been reached. So here we have 0.63 times Vs. And this time constant, we very often use a simple tau, and it happens to be equal to R times C from our equation and from our definitions up here. Now that was electricity, and we're going to talk about heat and moisture and air. So therefore, I'll now go to the PowerPoint, which I have over here. And if we take an example which you may have learned if you had our previous course on thermal building physics, we talked about a lumped analysis where we have a lump of material. For instance, a potato, which for some reason starts at 85 degrees centigrade and is put in an environment where it's 20 degrees centigrade. If the potato can be assumed to have all the same temperature, we consider it to be a lump. And this lumped analysis is a good approximation if the BO number, as you learned in that other course, is equal to, or if it's less than 0.1. The BO number is the heat transfer coefficient times the dimension of the potato and divided by the thermal conductivity of the potato. This means that the potato conducts heat so well that for practical circumstances, all internal temperatures within the potato can be assumed to follow the same value as it develops over time. And then we have a relatively large heat transfer coefficient, so that then governs, we have a relatively small heat transfer coefficient, meaning that the BO number will be less than 0.1. In that case, we had some mathematics in that other course that we taught about. There's actually a there's a differential equation that explains how the temperature develops with time in relationship to the ambient, the outside temperatures around the potato. And that is connected via the heat transfer coefficient for convection and the surface area of our potato. So this becomes kind of a contact thermally between the potato and the surroundings. That is in balance with how fast it goes to change the temperature, and that depends on the capacity of the potato, the specific heat, the density, and the volume of our potato. So all this we can put in another form of the same equation, but when we take all the coefficients gathered here, we could kind of use those terminologies I just introduced to have kind of a contact coefficient and a capacity coefficient. If the camera can follow me over here, then the contact that's something about thermal contact in this case, and that is 1 over, or the opposite of a resistance. So mathematically, it's somewhat similar here. So resistance should somehow be translated to 1 over the contact coefficient. Now, another form of our equation here, when we isolate, so we can isolate the temperature, how it develops with time, it comes here, and I've used the same original symbols, but I can now introduce also with the contact and the capacity coefficients as such. And here I've circled in those two in conjunction because they are also 1 over our time constant. You see 1 over capacity and over the contact coefficient. That's our time constant. Now, that was for temperature evolutions. What this slide shows, it focuses this slide on the capacity terms. That's why it's circled in here. And this was the thing we just talked about before. That was over here, sorry. With the volume of our potato or material, it's specific heat and the density of the material. So that was in this case a capacity coefficient, you could call it. If it were a room, we should look to the room's volume, again its density of air and specific heat of air. If we look to, that was for thermal things, but if we look to moisture, we could have some similar terminologies. And for instance here, we would be interested in vapor pressure as our driving potential for vapor pressure differences. And we're interested to follow the mass of vapor in a zone. So then we should look for a capacity coefficient, the volume of air, and then thermodynamically we should use the gas constant for water vapor and the absolute temperature. If it's for material, then we should have the volume of the material and the density of the material, and then the ratio between moisture content and vapor pressure in equilibrium with moisture. So that's something that comes out of absorption curves for building materials. And finally, we have something where we talk about changes of air pressure. If suddenly an air pressure change occurs, well, then we should again look to volume of air in a room, the gas constant for air and the absolute temperature of the room. Or we could look also for air pressures in a material. Then it becomes a little bit specific. That's about the pores in air, which I think I'll not go in detail with because this is rather special. But in principle, we have analogies for this capacity coefficient. The other part of the game, that was the contact coefficients. Before, we saw something about heat transfer from a potato, and we looked to the surface area of the potato and the convective heat transfer coefficient. That made the contact between the potato and its surroundings. Likewise, we can have, for a room, then we could take the room air and its surroundings. It's connected through the walls of the room or the building, ceiling, floor, and so forth. Each of them having a U value and an area, and we should add all those thermal contacts that they make together. And if we have an air change between inside and outside, also then the specific heat of air and the air change rate should be considered as part of making thermal contacts between inside and outside for heat. We could go through it also for vapor contacts between zones and outside, and also for those air pressure changes between inside and outside. Likewise, also for materials, they also have contacts between them and the surroundings for vapor with the convective vapor transfer coefficient, and also if there were some air built up inside of material, also like we could have it. The way to mention this is to say that we can, in either way, we can define a contact coefficient. And the point of this lecture, or this part of the lecture here, is that then we can always have the same mathematics. And just very briefly to an end, we could look to the case of an air volume in a swimming pool where suddenly we have a vapor production that starts. So we have an initial vapor pressure here, and then let's see how does it develop the vapor pressure with time after suddenly this vapor production starts. So then we look to the vapor pressure development per time, and in front of that we have, as I showed on the previous slide, we have a coefficient which becomes a capacity coefficient. This is kind of made in contact between inside and outside vapor pressures, so we should have a contact that explains how well is the vapor in the swimming pool diluted, you could say, by contact with the outside air that we have here. And this we call then our contact coefficient. So this would be the symbol for this. Always we have the same, again, capacity and contact coefficients to govern our problem when we have translated it like this. Now, this will give us a solution for the vapor pressure as it develops with time from its initial or external conditions and how it builds up over time. And again, we have the same mathematics as we've had before for all this. I'll just dwell briefly here, coming to an end, on this term that we have in front of our bracket here. And that happens to be the change of vapor pressure we will have from the initial condition until the condition we'll have in the end. So that could be different depending on the problems that you have, that you're dealing with. Then you could have various coefficients here, but always regard them to be the change that will occur from initial to final condition. Then that also makes kind of a universal translation. And with this, I think I've completed this talk. And to complete like we do sometimes in Denmark, snip, snap, snude. Nu er den historie ude. Or just to say it very briefly in English, that's all, folks. Thank you for this.